Easy? Really easy? Feel ripped off? All right. Any questions on anything? All right, let's get talking then. So, everybody's got their cell phones and computers put away. Nobody's listening to their hip hop music, their EDM. All right. Honestly, I would really enjoy having a earplug right here and teaching you and then singing every song. All right, I want to go over a little bit of these square law equations a little bit more. I'm going to also start on small signal analysis today. So, I haven't said that I'm going to do that. All right, so let's go. Why don't we start out by doing a simple example and making sure everybody understands. Well, first off, what do you think today's quiz is going to be on? Well, not really CMOS. IV curves. IV plots. No one's going to mess them up like I did, right? All right. All right, so let's go do a simple example. And the point of what I'm about to tell you is I want you to have a feeling for what's going on. Okay, so I'm going to go through this kind of slow, but I want you to develop a feeling for what's happening. We'll support the feeling with math. But let's start out with this simple circuit right here. And let's say this has a WP over LP. And let's say there's a current flowing through there. And we'll just call this ID. And I want you to calculate, let's just say we're using the long channel process, whatever, that's VDD. And I want you to tell me how to calculate this voltage, which I'm going to call V bias P. How do I approach this problem? Right, so how do I go from there? So I say VSG because it's a PMOS, and I write plus minus VSG is equal to the square root of 2 times ID divided by KP sub P times WP over LP plus V threshold P. Now I purposely wrote it not the normal square law equation, but a little bit different. So you would get to using that equation to calculate the voltages with the current. So everybody see that's just algebraic manipulation. So now, if I ask you what is V bias P? I didn't calculate V bias P, right? VDD minus VSG. VDD minus VSG is V bias P. Everybody cool with that? And so now, I'm going to come over here, and I'm going to put that voltage into a MOSFET of the same size, WP over LP, down into a resistor. And I'm going to assume the MOSFET's operating in saturation. Okay? Calculate the current that flows in this device. So, what is the source to gate voltage of this MOSFET? It's the same, source to gate right here, right? Source to gate would be VDB minus V bias P, or the same VSG. Everybody follow that? So what's the current that flows if I have that VSG? Don't think deep. ID. This current over here is mirrored over here because of the VSGs. This is called a current mirror circuit, and it's ubiquitous in analog IC design. Everybody follow? Any questions? Because I want to do an example now. This is the R. And well, let me ask a simpler question. What's the voltage right here? ID times R. Now, here's the question. What's the maximum value of R that I can have for this MOSFET to stay in saturation? What's the maximum value I can have of R for the MOSFET to stay in saturation? So let's start out just asking some simple questions. If R is 0, what does that mean? Yeah, it's a wire. So the drain voltage is what? Drain, gate, source. The drain is 0. So if R was 0, the drain is 0, and the MOSFET would be in saturation. Everybody follow? Wait, before I go on, was everybody able to prove that this device is operating in saturation on the homework? That was today, right? Oh, that one's due on Wednesday? Why don't I do it for you real quick? Or should I? James says no. All right, what is the requirement for this to be in saturation? There's two things. Well, let's start out with VGS has to be greater than the threshold voltage, which means there should be a current flowing, right? If it's going to be in saturation. So VSG has to be greater than threshold. Remember my analysis or my analogy last time? I turned the knob to the point where water starts flowing in the hose. That's this one, right? ID versus VSG. Everybody cool with that? Okay, so now the other one is what? Minus V threshold P. Now, would everybody be okay if I wrote that as V source minus V drain greater than or equal to V source minus V gate minus V threshold P? Would everybody be okay if I went boom, boom, and I wrote V drain less than or equal to V gate plus V threshold P? But what is the relationship between the gate and the drain in a gate drain or diode connected device? Everybody agree with that? So wouldn't those cancel and I would have to be 0 less than V threshold P? So doesn't that, if VSG is greater than the threshold and it's gate drain connected, doesn't it have to be in saturation and a current's flowing in the device? Does everybody follow that? Now I want you to burn that into your heads because we use that all the time we'll use it in example 9.5, which we'll talk about next time. We use it all the time for the load. It's a diode connected load for our current mirrors. So it's like the load in a diff amp. It's one side. Okay, any questions? So now, going back to this side. If R is really small, the drain voltage is really low and the device is in saturation. However, as R goes up, what happens to this voltage? Starts going up. And then when I look at this equation, the source to drain voltage, well, let's pause. The source to drain voltage is this voltage right here, right? The source is at what potential? VDD. And as the drain voltage starts going up, what happens to VSD? Smaller and smaller and smaller, and this is no longer valid. VSD is not greater than VSG minus V threshold P. Does everybody see that? So there's a maximum value of R that I can have before this gets too high in the device triodes because this voltage gets too close to VDD. Okay, so I'm going to redraw the circuit on the next page, and then I'm going to use just the parameters from the book, and I'm going to calculate, and we're going to calculate the maximum value of R, which is a good quiz question and a good homework problem. All right, I have that all the time. All right. So let's put in these numbers right here. Let's use our long channel process. 30 micron by 2 micron. And if I remember correctly, 20 microamps, which I should remember, but let me just double check. Now note, it's only valid for these particular sizes. And so let's calculate, let's say plus 5 volts. Let's calculate this value first. So I'm looking at the back of the book or the table in chapter 9, and I write that VSG equals the square root of 2 times 20 micro divided by 40 micro, and the 40 micro is what? 40 microamps per volt squared? Kp sub p, transconductance parameter of the p channel, times 30 over 2 plus the 0.9, because the PMOS threshold is 0.9, the NMOS threshold is 0.8. Okay, so I plug this in, I say, okay, what can I do? Boom, boom, 2 over 30, I'm having deja vu here. That would be the square root of 2 over 30 plus 0.9, which I believe is roughly 1 over 15 or 1/4, 0.25. So I'm going to just round it to 1.15 volts. Slightly more than 0.25, roughly 0.25. Any questions about that? Anybody agree with that? All right, so I get 1.15 volts. So what's this voltage? 3.85 volts. Then I come over here, I want to pick the same size device, 30 micron by 2. And for the resistor, I'm going to start out, I'll just pick R, and then I'll put this voltage as, what do I write this voltage as? (20 microamps times R. I'm going to write that as V sub D. And then I'm going to ask, what's the maximum value that I can have for R? So I know in this case that VSG is greater than the threshold voltage. So I write that VSD has to be greater than or equal to VSG minus V threshold P, or VD has to be less than or equal to VG plus V threshold P. Looking good? Or why don't I just use this directly instead of using this? Yeah, let's not. Yeah, let's do it. Nah, who cares? All right, we'll just say V drain is less than V gate plus V threshold. What is V drain? Then that has to be less than VG 3.85 plus 0.9, which is less than 4.85 if I did it 75, or VDD, what's called VSD sat, where VSD sat is this thing, and VSD sat is another way of writing it is VSG minus V threshold P. I just went over a bunch of things we're going to use throughout the rest of the semester there. This is also called the excess gate voltage, or we're going to call it the overdrive, and we're going to use this a lot because it's really an important parameter in analog design. So if you look at that, that's the voltage there, which is called the overdrive, or the excess gate voltage, the voltage above the threshold voltage, or VSD sat, or the minimum voltage you need between the source and the drain, blah, 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 that I use as a design parameter. It helps determine speed, helps determine output swing, helps determine gain. So it's a super important parameter. Before I move on, would everybody agree then, just to finish the problem, I don't want to get partial credits, that R has to be less than or equal to 4.75 over 20 microamps? Everybody agree with that? And let's put a box around our answer. I'm sure the grader will appreciate that. All right, any questions? I've got a lot to review here. Does everybody understand that by the R becoming too high, the drain voltage grows and that MOSFET, the PMOS, goes into triode or leaves saturation, or if you want to call it linear or ohmic, I don't know what you learned in 320. I always use triode as an vestige from vacuum tube days. Any questions about that? All right, and any questions about what the excess gate voltage is? Yes. Not on this?
It's about ID. How was the channel length modulation?
I might go over that, man. Hold on. That's on my agenda. Don't worry. That was my next topic. All right. So you understand that VSG is 1.15 volts, which is the threshold voltage plus this term. So you have to get a voltage at least equal to the threshold voltage, and you want to go above the threshold voltage, or you want to exceed the threshold voltage, and that's what this is. This is how much you overdrive the threshold, above the threshold, or it's in excess of the threshold voltage. So that's this term right here, which is roughly 0.25 volts. Does everybody follow that? Does that make sense? So this is a parameter when we do our designs. We want to make sure this is large enough for certain things, or small if we want other things. Okay. Now, if I were to go back here and we were to do this problem again, now that we've learned this, we would say, oh, this is roughly 0.25 volts. And so I would say VSD sat is equal to 0.25 volts, or V overdrive. And it's very confusing because the same thing's called lots of things. And then you would say, oh, if VSD sat, which is VSD sat, so we want VSD greater than or equal to VSG minus V threshold P, or greater than or equal. What's another name for VSG minus V threshold P? VSD sat. So we need this voltage to be at least 0.25. So that means this voltage is 5. That means this voltage has to be below 4.75. Looking good? Any questions? So I've got a MOSFET in the middle of a circuit, and I calculate, I do the bias, and I get, oh, the voltage, the VSD sat is 0.2 volts. That means the minimum voltage I need across that MOSFET to be in the saturation region, in this region, is the 0.2 volts, because I'm right there at VSD sat, and I need to be out here. That leads me to Francisco's question, but before we leave that, are there any questions? All right, so if I look at the MOSFET curve, and you remind me, this is VSD and ID, and I get a curve that looks like this. Tell me the situation at home that this corresponds to. Turning the valve on at your house, new construction. Well, it's VSG, but then I go out into the street and I turn the valve on in the street, and as soon as I get pressure to my house, the water starts going through the valve, going out, cleaning my plumbing out, tell the valve isn't on enough, and it flattens out. Right? No one's going to replace a water heater and before they turn the power on, not make sure it's filled with water, right? You understand? You replace, you have to drain your water heater, you put the new one in, you connect up the plumbing, turn the power on, and then about 10 minutes later, boom! Why? Because the water heater is filled with air. You haven't filled it up with water. You got to flush out the system. Water heaters don't like to be on unless they're full. All right? Of course, nowadays, I think they probably have safety mechanisms. All right, so this voltage here going down is called what? VSD sat. And then VGS, whatever the VGS is, and this has to be greater than the threshold voltage. Okay, so I got a question. Today on today's homework, you got, oh, I'm at 12 microamps when I calculated my current. But Spice told me that I had 14 microamps or whatever it was. Well, wait a sec. So I had this kind of configuration in the R, and I calculated 12, but now I've got an R here, and depending on the R, if R was really small, I'd be up here with the large VSD. But if R is bigger, I move down here. And so I'm moving up and down on this curve, or up and down on the channel length modulation curve. And you'll see, especially in the 50 nanometer process, that this curve can be huge. It can be like this. And so you can get huge amounts of variation in the current, even at the same VGS. In other words, the square law models are really limited because of this. And I'm going to derive the small signal models later today for the output resistance using the channel length modulation parameter. However, here I want to write the equation to include channel length modulation if you wanted to include it with your hand calculations today. So let's say that, and I'm going to give you some example numbers. So we got ID equals KP sub P in this case over 2 WP over LP times VSG minus V threshold P squared. And now to include the extra current, I'm going to write this term right here, 1 plus lambda, and this is the channel length modulation parameter. With units of volts per volt times VSD minus VSD sat, just like that. Now, this equation assumes VSG is greater than the threshold voltage and VSD is greater than or equal to VSG minus V threshold P. Okay, so does that equation, does that stuff next to the channel length modulation parameter, does that VSD minus VSD sat, does that ever become negative? No, because that equation is for saturation and it's only valid when VSD is greater than or equal to VSD sat. Does everybody see that? And so let's think about it for a second. If VSD starts to go above VDS sat, which is equivalent to saying what?
Saturation.
Yeah, the MOSFET's moving more into saturation. It's moving up the curve. VSD starts going above VDS sat, I'm moving up, right? And then my current's going to increase, and it increases by that parameter lambda. Okay, so now I say, hey, wait a sec, let me just throw some numbers. I did today's homework, and this was, I calculated using this term, 12 microamps times the 1, plus, let's just put a number in here for lambda, I don't know what it is, 0.02, let's say, all right? Let's say I have 0.02, and I'm 2 volts above VSD sat, so I'm times 2. So that would be 0.04, or 0.04 times, or I'm sorry, 0.04 times 12 microamps. It's probably more than that. And what is that? That's half a microamp. So with that simple number, I'm getting a half a microamp error just due to this lambda. And let me just look in the book and see for this process what we simulated the lambda to be. And it is, you know, I came in early today and I reboot this computer and I did this. And it's still, yeah, whatever. All right, so here you get 0.0125. I use 0.02 times 2. So and then times whatever this current is. That gives you the slope of the line. I'm going to go over the small signal parameter and output resistance. Again, one other thing that in these models, they're not this simple. They're really complicated because as you apply larger voltages, for example, you get all these second and third type effects which change the accumulation of charge and how it's accumulated in different places in the device. So even like 10 years ago, the square law equations were really, really limited. And you might ask, well, if they're limited and they don't give really close results, why do you include them in your book? And the answer is, well, you need students when they're learning to learn how to design things practically where you use charts and you read things off, but you also need students to get used to doing mathematically rigorous problems where they do calculations. And so in real life, when you get a process design kit for a process, you look at the transistors, they show you the curves, but the models are like 150 parameters. You can't do hand calculation. So you look at the plots and you go, oh, I want to operate right there. And then you go, oh, that's at a gate to source voltage of this and a drain current of this. And that's what you try to get. But if I just said to students, just look at plots and plug in the numbers, you don't get mathematical rigor. All right. And so that's why there's two processes in the book. And we use the longer channel and the hand calculations. We will rarely do anything with the shorter channel devices in the square law equations, if at all. Okay? So everybody got that. And the frustrating thing is that when you do your, like today, you do it, like I got 12 and it's supposed to be 14. It says 14. Guess what? Change the resistor value. Make it a smaller resistor so you get a larger VSD and you go more, and I guarantee that current's going to go up. Make it a bigger resistor value, and I guarantee the current's going to get closer to the value you calculated. You understand? So it's not, it's you're making the transition from, you know, oh, circuits, I got 1.05271 and it's precise and everything works, to actually practical stuff where things don't have a precise number, and when you calculate, they're not going to give you what you exactly calculate by hand. Does that make sense? That's real life. I mean, things vary. All right, any questions on these problems? I want to go over one more thing before we talk about small signal, or we start small signal parameters. Okay, so I want to talk about injecting and stealing currents, because that's part of your next homework problem, and I want you to intuitively understand this. So let's say that I have let's not worry about how I do it, but let's just say I have a battery here, and I have a resistor, and I'm just going to put some numbers in here, and let's use our 20 microamps. And I look at this, and I've got 20 microamps flowing down and 20 microamps flowing out. KCL is held, right? What goes into the node comes out of the node. Everybody follow that? Now, I want you to think of the following. You connect a circuit up, and we're going to do this in this class, and it steals current. Let's say, just put a number in there, let's say we steal 1 microamp. What happens? Obviously, KCL. This one goes to 19. But what happens to this voltage here? Goes down. Let's say I steal 10 microamps. Can I do that? Yeah. I steal 10 microamps. What happens? The voltage goes down even more. Let's say I steal 20. Does everybody follow that? Let's say I steal 20 microamps. Got 20 coming out here, 20 going out here. What's going to be the current flowing in that? 0. So if there's 0 current flowing in there, people that took circuits from me, what is that voltage? 0. I'm sure everybody knew that. I just went up and checked my, or dropped some stuff off in my office, and I got a email about student suggestions for the programs and all that, about all the different things they recommend. Yeah. All right. All right, they said more discussion sessions for EE 220. No, they didn't say that. Yeah, the 221 students this semester, I'm not involved in the lab and I already know what's going to happen. Yeah. All right. I'm involved in this lab, but man, your guys are working me. Okay, so everybody gets stealing current. Let me ask this. Can I steal more than 20 microamps here? Yes, I can. Let's think about what happens. Let's say I steal 30 microamps here. There'll be 10 microamps flowing there, 20 microamps flowing there, and this voltage will go negative. And I want to pause and ask, is that okay if this voltage goes negative? I want to sketch the cross-sectional view of the PMOS. So I sketch the cross-sectional view of the PMOS, which is in your homework due on Wednesday. And there's my N well, and it's tied to VDD. In case you haven't had 421, or wait, let me ask the people that did have 421, what does that, how do I modify the schematic here to show that? The well being tied to VDD. Boom. The body, the fourth terminal goes to N well. That's the body. This is the body of the device. You got to have that to the highest potential. Then I go over here to P plus, gate, source, drain, and then I ask, all right, are there any parasitic diodes? And what do I mean by that? There's some diodes built into this transistor that are there no matter what. And I go, oh, they're right there. And this is at plus 5 volts, and then I've got one here too I'm not going to draw on there. Yeah, maybe I'll draw it. How about I draw it like that? So I got this at VDD, or 5 volts. I'm pulling this negative with this situation. Does that turn that diode on? If this is at 5 and this goes negative? No. Let's think of intuitively. I've got my pipe. There's my flap. I know my diode only lets water go like that. And I've got a positive potential here. Then I've got a negative potential here. And the positive pressure would try to push current through the diode backwards. Positive potential here, negative potential here, and try to push current through the diode. So it's more than fine if that node goes negative. Did anybody get that? I understand the words coming out of your mouth, but I don't understand what they mean. All right. Do you follow that? Did you learn about drawing the cross-sectional view in 320 like this? Did you learn about MOSFETs? All right, well, this is the cross-sectional view of the MOSFET, all right? And so you have a P plus there and then an N. And hook up with somebody that have 421, like your neighbor there, and let them tell you how to do it. And then when you get it wrong, blame them and throw their homework at them. And, what the hell, you're no good. Okay. So let's go the other way, unless there are no questions on this one. So when you look at these, you just have to decide, if I apply X potential here, am I going to forward bias something? That's all you're looking at with the PN junction. The well's always at 5. If I diode connect the transistor, this would be at plus 5 volts. which is the well, and I know these are the source and the drain. And I say diode connect would be a connection like this, and I'd think of this as a diode like this, where this would be like some voltage, that would be some voltage. When this voltage gets higher than this one, the current flows. When this voltage gets higher than this one, wait, how do I know this voltage has to be higher than this one, or the gate, in simple terms? You got to get above the threshold voltage. Do what we're learning. Draw the source gate, and then you go, oh, to turn that on, VSG has to be greater than the threshold voltage. Draw it on there, that means, hey, the source has to be 0.9 volts greater than the drain. Draw it on there. That helps. All these things that we're doing, it's going to be useful if you sketch it on the schematic. Any questions? Yes?
Before we talk about the maximum and the minimum voltage, the settings that you have out there, you have reverse bias. What would be the minimum maximum voltage that you put in that drain before it breaks down? Can you break it?
Well, did it say talk about breakdown? Okay, well, that's set by the physical size of the device, and so it'd be the reverse breakdown voltage of the PN junction. Or remember in 421, which I don't want to get into now, the punch-through voltage, where the source, the electric field from the source and drain punches through and the current goes up. So, but for that problem, it's just saying, hey, if this is at 5 volts, what's the maximum voltage I can have on the source? 5.6, where that turns on. Same thing here. Hey, I can't have above 5.6 there. Oops, I'm giving you another answer. Man, you're going to be like disappointed how easy the homework is. All right. Any questions before we go inject a current in there? All right, let's go the other way. Wait, so before I leave this, key takeaway, I steal current here. What happens to that voltage? Goes down, I decrease. What happens to the current in the MOSFET? Neglecting body effect. Stays the same. How do I know? I'm not changing the source to gate voltage. Source to gate voltage fixed, current fixed. Think that. Hey, I got this hose bib on. I got it at a certain level, then the water coming out should stay constant. Okay? Unless I put more resistance on the end of the hose, and then I slow down the water until I put so much resistance I don't let the water come out, and then it goes into cutoff. Shuts off. Okay. Did anybody watch the video from the lab? And I want you to say no. I want to like, you know, it's a dangerous precedence because now in the future, you did it last time. Don't you like us? Yeah. Okay. All right, so let's do the same thing here. And then let's put our resistor here. And then in this case, I'm going to inject a current in here. And so I've got a current flowing here of 20 microamps, a current flowing here of I, a voltage that's what is the voltage here? Right on. Everybody follow that? Okay, so now, what happens is I inject the current in there. This goes up. Okay, it goes up, and please tell me what happens if this voltage goes too high. And you start going, oh, we're leaving saturation, we're going to triode. When we go into triode, what happens to the current? No, you're sliding down the slide, man. You're pushing current in. You push current, you reach here. This current starts to drop. So that means this voltage all of a sudden is getting really close to VDD. Keeps going up. What's the maximum voltage that I can have there? What is it? Let me draw the parasitic, let's draw the VDD on there and draw that parasitic diode that I just drew a couple of times. What's the maximum voltage I can have there? So I keep going up. This gets to 5.6. The diode turns on and clamps the node to 5.6 volts. So it goes to 5.6, and then this voltage won't go up, and any extra current gets sucked off in through the diode up the VDD and charges VDD. Does everybody see that? Does anybody see that? Let me do it again. Let's sketch here. So we have, let me sketch the diode on nice and clear. What's the material for the gate, or for the source or drain of the PMOS? P. It's a PMOS. Source and drain or P channel is P. That's why it's a PMOS. So then I go up here and I say, hey, there's my diode. This is P. This is N. It's going to my N well. And then I say, I've got a current I'm injecting in here. And then this wants to source 20 microamps, but as I keep injecting more current, this voltage goes up, this shuts off, then all that current ends up going here. Well, some will go down here, 5.6 or 7 over R. And then it goes in here, and then I keep increasing the current, and this gets clamped at 5.7 volts roughly, because all the extra current flows through that diode up there. Questions? Does that make sense now? Yeah.
So as the current keeps going into the diode, that will automatically be 5.7, and the other current will go down.
Yeah, the current that I inject, 5.7 or 5.6 over R, will go down. The parasitic diode from the source or from the drain to the end well will turn on, behave as a clamp, and that'll clamp that node to 5.7 volts. And then as I increase current, the diode will just turn on more and then pull the current off the VDD. Yes? There isn't a minimum voltage. You can go to a really small voltage as long as this resistor isn't made with a material that cares. You can go to whatever you want. And ultimately, you would have limitations on the maximum voltage across the MOSFET. All right, questions before we talk briefly about small signal parameters, and we'll continue on small signal parameters next time. Did anybody watch the video last time? How was the size? Better than the old ones? All right. Yeah, I know. I was just asking them, man. Go ahead.
Is there an application that you would specifically use that? Or is it just one of those things you kind of have to live with and come back because of your
That's a good question. There are applications where you use that diode, especially in power electronics, because it can act as a freewheeling diode which will remove energy from an inductor and cycle it back to the power supply. Does that make sense? All right, any other questions? Is this hard? Not. What? All right. I think it'll be fine, but what do I know? I think today's quiz will be fine too, but what do I know? I couldn't work today's quiz, so maybe you can't. But you probably can. All right. So I want to talk about small signal parameters. And I'm going to go through this because I guarantee that, like, probably everybody in here doesn't understand small signal parameters. And you will. Give it a week. All right? So I'm going to show you the curve that we talked about, the ID versus VGS curve. And then I'm going to ask you, for the case when you're in your yard turning on the MOSFET, for the case when you're in your yard, here you are, I'm going to draw you as a voltage that's variable, and go down, and that's VDS, and that's E constant. That's the water pressure to your house. And I ask you, vary VGS, turn on the water, and plot ID. These are very common interview questions. So you get this, sketch the IV curves for the MOSFET. There you go. Turn on vary VGS and plot ID. Tell me what to write.
Kind of think where your VT, your threshold's gonna be at.
Well, it's going to look like a diode, right? I'm going to turn until it starts to turn on, and the water's going to come on, or the water's going to come on and go up. Anybody not able to draw this? Who'd you take your electronics class from? Dr. Baker. And you can't draw this curve? You need to demand your money back. See how the fear is high? Everybody follow that? Okay, now, everybody understands that when I'm out here, I've turned the hose bib on and water's coming out of the hose, right? Now I'm sitting right here. I'm going to call this point my VGS, and your older books may have called it VGSQ for quiescent. And here I'm going to call it ID, and they're DC parameters, or IDQ. So I've turned the hose on. Water's coming out. That's called biasing the transistor. That's biasing. That's what it is. Now, imagine I take the hose, the handle, and I start to wiggle it back and forth, staying around where I have it set, but I go a quarter turn to the right, then a half turn back to the left, then a half turn to the right, then a half turn to the left. And I ask you, what happens on that curve? The water's going to do this, right? It's going to go back and forth like that. Everybody follow that? That little variation, that quarter turn if we're going peak or half turn if we're going peak to peak, is an AC signal, which I'm going to call, notice the change in the terminology, VGS. Lowercase. This one was DC, this one was AC. Everybody got that? I'm going to go surprisingly over here, and I'm going to call this ID, AC and DC. Any questions about the terminology? Yay or nay? So now, you know when we do an AC analysis in electronics, that's a small signal analysis. SPICE is saying, hey, I'm assuming the user is smart enough to know that that AC component has to be small compared to the bias point or the DC point. That AC current has to be small compared to the DC current. But I could actually, in my AC analysis, put 1,000,000 volts for VGS, and it would simply assume that it's multiplied or it's moving appropriately by the same amount as if I put 1 millivolt, because it's a small signal analysis. Okay? So when you use small signal analysis, you're assuming that things are small compared to the DC or bias point. Now, when you design, if you get a job designing audio products like headphones or amplifiers for cell phones or things like that, small signal analysis is really limited. Because imagine what happens for listening to louder music when you've got to go further up on the curves. Well, it's no longer linear, right? You can't simply treat the signals as small and linear around a point, which I'm going to do in just a second. Does everybody follow that? And so you have to use transient analysis, or you can use what's called a harmonic analysis to look at the total harmonic distortion of your amplifier. Okay, but for now, most of what we're going to do in this class is small signal analysis. And if you think about it, remember when we did op amps, we assumed the two inputs are equal? We're going to go through that. We're going to design an op amp in this class. We're going to find out there's little teeny voltages there, but they're really small. And so small signal analysis works really well. Now the output stage, it doesn't work so well, and that's where the distortion's added. Well, let's go ahead and do transconductance. And I'm going to define transconductance right now, and I want to make sure that you understand it. Transconductance, don't forget this, what I'm going over right now. Transconductance is the slope of this curve is the transconductance, or 1 over the transconductance, GM. So whoops, I got that back. Slope is GM. So if I ask now, what's the slope? You say, oh, gee, you're not challenging me. It's the rise, the AC, over the run, the VGS, and that's equal to GM. I'm assuming it's linear. So it's small and it's around a point. Everybody got that? So then I write, and for some reason students always forget this, ID equals GM VGS. So if I know the AC current or I know the AC voltage, I can use the transconductance to determine the other. So now I'm going to switch pages and derive this using a transistor circuit. Any questions? All right, let's do it. So I'm going to put my transistor in a configuration where I've got it biased so that there's a water source, a VDS, it's in saturation. I need that or it won't work. I'm also going to add a DC value to bias the transistor on. That's me turning the knob. And then I'm going to add an AC value, which is me wiggling it after it's on. Does the order of these two matter? Nope. And you know what I'm going to call this voltage here? I'm going to call it VGS, which is the DC plus the AC. So you see how tricky I was? I used lowercase, uppercase, then I used uppercase, uppercase, lowercase, lowercase. But the overall VGS is the sum of the two. Then I'm going to write the current that flows is ID, which I use lowercase, uppercase. That's equal to the AC component plus the DC component. I know most of you have seen this and already mastered it from your 320 class, right? Feeding my phobias. All right. Does it bother anybody? What's the AC component of the drain to source voltage? If I ask, what is the AC value VDS here? 0. Not changing the drain or source voltage. Okay, so now my only equation I know is the following. ID equals, let's just write it, beta sub n over 2, where beta sub n equals Kp sub n times W over L. And that's times VGS minus V threshold N squared. And now what I'm going to do, here's where I cringe UNLV calculus. I have my ID and my VGS, and I draw my curve, and I go up here, and I'm operating right there, and I say, hey, I want to find the slope at around that point. Around the point of the DC VGS and the DC drain current. How do I find the slope around that point? Derivative of ID. I say GM is equal or defined as the derivative of ID with respect to VGS at ID equal to a constant and VGS equal to a constant. Anybody agree? And tell me in simple terms, not math, what does this mean? Just holding the operating point, bias point constant, and looking at the slope around that curve. Okay, any questions? Wait, you mean calculus is useful? And that's equal to the derivative of the following. And I'm going to be a little verbose. Note that that's equal to ID plus ID. I'm going to write it as beta sub n over 2 times VGS plus VGS. And this is what? AC and DC. You know, that's where they got the name, small signal analysis, AC/DC. Is that right? All right. Take the derivative of this, and what's another name for this? AC plus DC. So what's the derivative of x minus a squared with respect to x? 2 comes down and I get beta sub n. Then I get the derivative of VGS with respect to VGS is, yep, just V, well, wait, hold on. Let's write it, let's be very precise. And then plus the derivative of what's in the middle here, and what's the derivative of what's inside here? The derivative of this is, well, threshold voltage is 0. And then the derivative of VGS with respect to VGS is 1. Oh, whoops. Because it's AC. Just kidding. Okay, but wait a sec. I'm wiggling this a small amount and wiggling this small amount relative to the DC. So I'm going to approximate this and say this is approximately beta sub n with VGS minus V threshold n. I should put it on a new piece of paper. I can just see in 10 years people will be saying, he still uses paper. It's equal to, or approximately equal to, beta sub n times VGS minus V threshold n. And this assumes that VGS is much, much greater than VGS, which is the small signal approximation. So they assume you know that when you use small signal analysis. And this is our GM. Let's do a quick example. Anybody follow that? Or was that, you didn't tell me there would be math in this class. I didn't sign up for that. There wasn't math in 421, was there? There's always math in engineering. What's that?
All we had to do is lay out. There was no math.
Yeah, there was when we derived the IV curves and we integrated and all that stuff. All right, any questions on this? Let's use it as an example. So let's do the following to make it easy on me. And then we'll do our quiz. And then I'll get on a plane. Let's see, let's do 1 millivolt plus minus 1.05 volts, 10 by 2. And if you don't use microns and you do your sims, what's going to happen? You're going to waste a lot of time because it's going to say 10 meters by 2 meters. And there's going to be huge capacitances, especially if you're using AC or you're doing frequency response. So why don't I just put a voltage here, let's say 3 volts. And first I ask you, find the AC and DC currents flowing. Well, let's do the trivial ones. What are the DC voltages in the circuit? It's small, it's AC, Remember, AC goes up by a quarter turn and then down by a quarter turn, right? So now any questions on that? Let's find the drain current. 120 microamps all over 2 times 10 over 2 times 1.05 minus 0.8 squared, which equals, let me see, that's going to be 0.25 squared. 0.25 times 0.0625. And this would be 10 microamps. Anybody believe me? Yay or nay? Close enough? All right, you can check. Let's calculate. So the DC current is what? 10 micro. What's this DC current? Zero. What do I do now? Calculate. I'm going to do the AC analysis. What's the first thing I do? Calculate my AC small signal transconductance. GM. 120. Well, I also know VGS. I didn't even need that. So I get 120 microamps times 10 over 2 times 1.05 minus 0.8. Does anybody disagree that this is 10 microamps?
It's 19
Or 20, sorry. Yeah, 20.
Yeah.
You need to correct me when I'm wrong.
Okay.
Think it is something. 20 microamps. So then what does this end up being? 150 microamps per volt. And now what's the AC current? G, you're not challenging me. It's GM times VGS, which is 150 nanoamps. 1 millivolt times 150 microamps. Now I know the AC and DC currents. We ready to sim it? Let's see how fast I can do the sim. Wait, does anybody have any questions on this? Wait, that made sense. I'm not used to small signal analysis and AC electronics making sense. Yes? Yeah. The DC gate current's 0. There will be, in the small channel process, some leakage because of tunneling. And then for AC, when we have capacitances, we may get a displacement current for the gate current. But for DC in the long channel, it's 0. Ideally, it's 0. Here's a piece of glass. All right, so let's go here. Let's go to here. File, save as, lecture. Oh, whoops, I want lecture 2, example 1. And I thought I had an example here, but I don't, so let's do the following. Let's grab a transistor, NMOS4. Let's do it from scratch. Help me out. N_1U, 2U, 10U, control, control left click. No. Oh, I'm hitting the wrong control. There we go. I was hitting shift. Press ground. Press ground. Then grab a voltage. And I'm going to cheat since I don't want to spend the time. I'm going to put one here. I'm going to put one here. And I'm going to hit save. Minus, minus, minus. Oops. Press G. Wire everything up. You miss key bindings. They have them. Yeah, it's like F3, I think. It's right here. F3. What's this voltage? 3. Now this is what I'm going to cheat at. Instead of writing 2 voltage sources, I'm going to use 1. I'm going to call one 1.05. And the other I'm going to put at 1 millivolt. So I've got both of them. That's the same as both in series. Okay, now I'm going to do a dot OP to begin with, just to see how close I am to 20 microamps. It won't. Oh yeah. Don't let me forget that. That's what I forgot last time. I'm trained. Man, you guys have no idea how much time I put into that website. Holy crap. And you guys don't even use it. All right. So 17.4. What do you think is going to happen if I increase this voltage to 5? What's going to happen to the current? Moves up, right? What we went over in lecture. Everything I cover is useful. Just ask me. 17.7. Oh, it didn't go up that much. 0.4 to 0.04, 74 to 77. All right, so let's do the AC. But I'm going to do it a little different. I'm going to do it with a I'll do it with a transient. We got to go do the quiz. I'm going to use a transient just to show you. So DC offset is 1.05. Amplitude's 1 millivolt. I'm going to put a frequency of 1K in here. Then I'm going to change this to a dot tran, and we're going to go for stop time. Let's go 3 milliseconds. Time to start 0. Okay. Oops. Run. I'm going to plot the AC here, and no. Dot options. Plot win size. This is a little trick. Equals 0. This program's for switching power supply, so it likes to throw data away. See how the magic I know? So now you know the magic too. And then I'm going to add a plot. Is this right? Is this 1 millivolt of AC on 1.05? Everybody see that? Now I'm going to add a plot plane. Or actually, let's do it on this one. And I'm going to get a current that is 17 micro. And let's subtract actually the 17 micro minus 17.73 U. And then I calculate, oops, I'm off still. Minus 17. Oh, plus, sorry. And you can see it's pretty close to the 150 nanoamps that I calculated. I didn't really put it in precisely. I'll leave it at this and you can play with it later. I'll post this as usual.